Let us look at a few more problems on Faraday's law. We have a rod, the length of which is 0.8 meters, rotates about an axis through one end and perpendicular to the rod with an angular velocity of 10 radian per second. So that is the axis. So the axis is coming out of the plane. It's perpendicular to the plane. And this rod is rotating like that. The plane of rotation of the rod is perpendicular to the uniform magnetic field, whose magnitude is 0.5 Tesla. So the magnetic field here is represented by these crosses, meaning the direction of the magnetic field is into the plane, and the magnitude is 0.5 Tesla. What is the induced EMF in the rod? What is the magnitude of it? We know the EMF can be calculated from this expression. It is pretty much the rate of change of magnetic flux through an area. Let's first calculate the magnitude of this EMF. So we're just interested in that quantity. Now we note that in this particular problem, the magnetic field is not changing. It is pointing in the same direction with the same magnitude. So since we know the magnetic flux in this case is given by BA, B is the magnetic field and A is the area through which the flux is calculated, substituting this expression in there, you see that the magnitude of EMF is quite simply B dA dt. Now, area is indeed changing. How so? As this rod rotates about this axis, it goes like that. And in that process, it will trace out or sweeps out certain amount of area. And that area is given by this shaded region. Let's call that A. And it moves through an angle. Let's call that angle theta. For a segment like this, a pie-shaped segment with radius, let's say L, and angle is theta, the area of this pie from geometry is quite simply half the radius squared times the angle in radian. So when you substitute that expression in here, you get B. Now L is not changing. L is the length of the rod in this case. It can be taken out together with the half like that. D theta dt. D theta dt is the rate of change of this angle as the rod moves, and that is quite simply the angular speed, omega. So the expression for the EMF generated will become BL squared over 2 omega. We know the magnitude of the magnetic field, which is 0.5. The length of the rod is given by that 0.8 meter, don't forget to square it, over 2, and omega is 10 radian per second. And that will give you 1.6 volt for the EMF. This is the magnitude of the EMF. What that means is there must be a potential difference between this point and that point, with the potential difference being the same as the EMF, 1.6 volt. Now the question is, which point is at a higher potential? To answer that, let's look at this rod construction and let's concentrate on a free electron within that rod. So this is a free electron. As the rod moves like that, we know that this electron would have a linear tangential velocity like that. So that is the velocity of that electron. And keep in mind that it is moving in a region where there exists a magnetic field in that direction. So what is the magnetic force on this particular electron? We know the magnetic force on a moving charge is given by QV cross B. when you cross from V to B, your right hand thumb will be pointing in that direction, which would be the case for a positive charge. But what we have here is an electron, so it's a negative charge. That means the force on this negative charge must be heading in an opposite direction, that way. So the electrons within that rod will tend to move in an upward direction and accumulate there. Over time, the top end of the rod would be negatively charged, and the lower end of the rod, where the axis is, will carry a net positive charge, like that. So the answer is, this end would be at a higher potential than that end. And the potential difference is given by that number, 1.6 volts. Problem 2. A flexible circular loop, 0.2 meters in diameter, so that is this circular loop right there, lies in a magnetic field with magnitude 2 Tesla. So again, these crosses are the magnetic field. It's going into the plane. The loop is pulled as shown below by the arrows, meaning in this direction, so as to change the effective area of the loop. Now this makes the area of the loop to reduce and finally go to zero at 0.3 seconds. Find the average induced EMF and also what is the direction of the current in the circuit. Because we note that the magnetic field ends at that border. So this is field-free region, and the magnetic field exists only to the left of this dashed line. The induced EMF is given by the Faraday's law minus the rate of change of magnetic flux through that loop. We note the magnetic field does not change. It points in the same direction with the same magnitude all the time. So that magnetic field can be taken out of the derivative sign, leaving only the area there. So let's calculate the change in area over time. Now we note that we can compute this by looking at the area final minus the area initial over the time, which is in this case 0.3 seconds. The final area is 0 because the loop goes to 0. The area of the loop goes to 0 in 0.3 seconds. So the final area is 0. The initial area, this is a circular loop, so circular area is pi radius squared. The diameter is 0.2 meter, so the radius is 0.1. Square that over 0.3. Substituting this in here and using 2 Tesla for the value of B, and noting that this negative will cancel that negative, we end up with a positive EMF, and it is 2 for the B, pi 0.1 squared over 0.3, which will give you 0.209 volt. So that is the average induced EMF in this case. Now let's determine the direction of the current in the circuit. Before we do that, we need to know the direction of the induced EMF. So let's resketch this diagram like that. So this is the same loop, and I'm looking from the side view by rotating this entire system like that. So the magnetic field is going like that, and the area vector is also going like that. So the positive EMF would follow that direction, and since we indeed have a positive EMF, that is the direction of the EMF and also the direction of the induced current. So going back to the original diagram, this direction for the induced EMF means like that. So that is the direction of the induced EMF, and the same is the direction for the induced current. So what that means is the current goes like that. through the circuit. That is the direction of the current in the circuit. And that solves the problem. Thank you for watching.